While I was at it today, thought I would take advantage of the beautiful day and the bike wheel to show you a couple other things about rotational mechanics. In this case, let's talk about the conservation of angular momentum. So if we take a look at this first clip here, I'm going to back that up this time. So I get the wheel spinning and I balance it on my finger, and lo and behold, it stays in its vertical spinning alignment. Well, what's up with that? All right, I want you to go ahead and press pause here. I want you to try to come up with your own explanation of why it's doing that. Now that you've had a chance to think about it on your own, let's talk about this. So the bicycle wheel is moving, therefore it has an angular momentum. Since it's on a greased axle, there are no other outside forces, or actually, since we're talking about angular mechanics, there's no outside torque acting on it. Therefore, it's going to have a tendency, it's going to conserve its momentum. So what that means is, since I gave it a momentum, by the way, by exerting a net external torque on it, I gave it a momentum. By giving it a momentum, now that there's no external torque acting on it, it's going to conserve that momentum. Remember that momentum is an angular, momentum is a vector quantity. So not only is it going to conserve the amount of momentum, it's going to conserve the direction. Since the direction, quote unquote, of this two-dimensional motion is has the axle vertical, it's going to have a tendency to conserve not just that motion, but also that direction. All right, here's another example of this. This is one of my favorite ones. So basically what I did is I tied this string to a tree out front, and then I tied one end of the string to the axle of the bike wheel, and I get it spinning and let go. And as you watch, you can see that it is only being supported on one side. It seems to be defying gravity. So again, why don't you take a moment and press pause and think about why you suppose that's happening. All right, now that you've had a chance to think about that on your own, let's talk about it. Again, I apply an external torque to give that object to change its momentum. And once it's got momentum, it's going to have a tendency to conserve that momentum. Now, another question I've got for you is, in this example here, we see that that wheel is spinning like that. This is that tendency, that behavior is called precession. That axle essentially rotating on its own. Then the question becomes, what causes that? Well, that comes from the fact that you have the vector momentum of the spinning wheel, and at the same time, since it's only being supported by one edge, this is tough to explain, but I'm gonna try to draw it. So if this is my string, and here's the axle, and there's my tire. All right. What's happening is I have a vector momentum that is pointed that way. That would be the angular momentum of that tire. All right. At the same time, what's happening, let me switch colors here so we don't get these confused. At the same time, and this is not a free body diagram because I've got an angular momentum, and then this is a force. You've got the force of gravity pulling down on that tire. That combination of that force in that direction acting on that angular momentum in that direction causes the tire to precess like it does. Because now you have a net external torque acting on that momentum, and so it's going to have a tendency to change that momentum, which is why that axle keeps rotating in space there. So anyway, hope this helps you understand angular momentum and the conservation thereof. As always,